Some vocabulary first, because these terms are used precisely in mock schemes. A bug is an error in a program causing it to behave unexpectedly. Debugging is the process of finding and removing them. A syntax error breaks the rules of the language. A logic error is code that is valid but does the wrong thing. And a runtime error is one that appears while the program is running, dividing by 0 or reading past the end of an array. Note that these categories are about when and how a fault shows itself, not about how serious it is. A syntax error stops the program from running at all, which sounds worse but is actually the friendlier kind. That is the distinction the whole lesson turns on, so let us be exact. A syntax error breaks the grammar of the language. A missing bracket, a misspelled keyword, a missing quotation mark. The program will not run at all, and the translator tells you where the problem is. A logic error is grammatically perfect code that does the wrong thing. The program runs happily and produces an answer, and nothing warns you. Compare them across the row. Does the program run? Syntax, no. Logic, yes. Is an error message produced? Syntax, yes, usually with a line number. Logic, none at all. When is it found? Syntax, when translating. Logic, only when you check the output or when a user notices months later. And that is why the logic error is the dangerous one. A syntax error is an obstacle, annoying, immediate, and it tells you where it is. A logic error is silent, and the program will confidently give you wrong answers for as long as you let it. Here is the error that appears more than any other, and I want to trace it rather than describe it. The algorithm is meant to total 3 numbers. Line 1 starts the loop, line 2 sets total to 0, line 3 inputs a number, line 4 adds it to the total, line 5 ends the loop, and line 6 outputs the total. Read that and it looks entirely reasonable. Every line is doing something sensible. But the initialization is inside the loop. Trace it with 10, 5, and 20. First pass, line 2 sets total to 0. Line 3 reads 10. Line 4 makes total 10. Second pass, line 2 sets total to 0 again. And there it is, the 10 is gone. Line 3 reads 5. Line 4 makes total 5. Third pass, total is reset to 0 once more. Reads 20. Total becomes 20. Line 6 outputs 20. And notice what makes this so hard to spot without tracing. 20 is a completely plausible answer. It is not 0, it is not an error message, it is a number of about the right size. The program appears to work. Anyone glancing at the output could accept it. The trace table makes the fault unmissable because you can see total returning to 0 on a specific line on every pass. That is what trace tables are for, and this is the fault they were made to catch. The second common fault is off by 1 loop bounds, a loop running 1 time too many or too few. For I from 1 to 9 when there are 10 items misses the last one. From 1 to 11 runs past the end of the array and causes a runtime error. The check is always the same. Count how many times the loop actually runs, not how many you meant it to. A loop from 1 to 10 runs 10 times. From 0 to 10 runs 11. The third is the wrong comparison operator, and it is a close relative of boundary testing from the last lesson. Greater than where you meant greater than or equal to. The program runs, most values behave correctly, and only values sitting exactly on the boundary come out wrong, which is precisely why boundary test data exists, and why normal test data would never have found it. The fourth is the infinite loop, a condition that never becomes false. Usually the counter is not incremented inside the loop, or it is changed in the wrong direction, or the condition can never be satisfied. The symptom is distinctive. The program hangs, produces nothing, and has to be stopped. When looking for one, ask whether anything inside the loop can actually make the condition false, and whether it does so in the right direction. The fifth is a swap without a temporary variable, which we met in the standard methods lesson. Writing a gets B, then B gets A, does not exchange them. The first assignment overwrote A, so the second one copies B back into itself, and both end up holding B's original value. You need a third variable to hold one of them while the other moves. If a question shows you a broken swap, that missing temp is what it is testing. Now, a method rather than hoping to spot the fault by staring. First, read the question and establish what the algorithm is supposed to do, because you cannot identify wrong behavior without knowing the right behavior. Second, check the structure. Are initializations before their loops? Do the loop bounds cover the right number of items? Does every branch of every decision do something sensible? Third, check the comparison operators against the wording. Over 50 means greater than. At least 50 means greater than or equal to. Fourth, trace it with small test data, 3 or 4 values you can compute in your head. And fifth, when the trace and your expectation diverge, note the line where they first diverge. That line, or the one just before it, is where the fault is. The reason to trace rather than read is that reading tends to show you your intention rather than the code, particularly when you wrote it. A trace shows only what is actually there. The worked example on the page finds a highest value algorithm with 2 faults, and it is worth seeing what a full answer looks like. Fault 1, highest is initialized to 0, which fails if every value is negative. The algorithm reports 0, a number that was never in the data. The correction is to initialize highest to the first value in the list and compare from the second onwards. Fault 2 is in the comparison or the loop bounds, depending on the version. And notice the sentence underneath the table. The algorithm would run without any error message. Both faults are logic errors. Nothing crashes and a plausible number appears, which is why the exam expects you to state the line, state what is wrong with it, and state the correction. 3 separate things, and answers that say the algorithm does not work get none of them. 4 things to take into the exam. First, distinguish syntax from logic by whether the program runs and whether an error message appears. And remember, the logic error is the more dangerous one precisely because neither happens. Second, when identifying an error, name the line, say what is wrong, and give the correction. All 3 because they are usually 3 separate marks. Third, know the 5 common faults by sight. Initialization inside the loop, off by 1 bounds, the wrong comparison operator, an infinite loop, and a swap with no temporary variable. Between them, they cover most of what an exam will show you. And fourth, trace before you conclude. A logic error is invisible to reading and obvious to a trace table, and the trace is also the evidence that supports your answer.